Hope you enjoyed a little bit of a break. This is now the second half of periodic trends. So we were looking at reactivity of metals and nonmetals and the trends on the periodic table. Before we explore that, we need to review a little bit. So what we learned about charges a long time ago, or a while back anyway, we learned about Coulomb's law, which is the force between charged particles. And in this case, of course, we're dealing with the nucleus and the valence electron. So just as a review, the force is given by the equation on the screen, Coulomb's constant, and again, there's two different charges. There's charge 1 and charge 2, but in this case, the charges are the charge on the electron and the charge on the nucleus. R is, of course, the distance between the charges, which in this case would be the atomic radius. So I pretty much just said what's on this slide. The big deal here, however, is that realize that the radius is squared and in the denominator, but the fact that it's the radius squared means the radius is going to have a very big effect on the interaction between the nucleus and the valence electron. And remember, we're talking about gaining and losing electrons. The only thing that holds that electron in is the nucleus. The only thing that can prevent it from leaving is also the nucleus. So this is a summary of how atomic radii vary as we go across a row and down a column, just using mostly the main group elements. Just note on this slide is still using some of the older numbering system. But as you can see, as we go across a row, atoms get smaller. If you look across the second row from lithium to neon, you can see they get significantly smaller. Going down a column in general, they get larger. So if you look, for example, from hydrogen down to cesium under column 1A, they get larger. Now let's look at why this is. All right, so there's really two factors that play into size of an atom. First of all, as we move to the right across a period, the atomic size decreases. That's because, as we said, it's the distance between the nucleus and the valence electron. Now the reason for that is, once again, reviewing electron configurations. So if you have a periodic table or your textbook with electron configurations handy, you can see it. In the same row, as we go across a row, the electrons that are being added are going into the same energy level. So for example, in the second row, lithium, beryllium, boron, all the electrons that we're adding are going into the second energy level. Lithium is 2s1, beryllium is 2s2, boron is 2s2, 2p1, and so on. The second energy level is, in general, about the same distance, but as we go across a row, we're also adding protons to the nucleus. So more protons in the nucleus, a bigger positive charge, is going to tend to pull everything else in, because the second energy level is pretty much the second energy level. So as we move across a row, we're having a more positively charged nucleus, which is pulling the valence electrons, actually all of the electrons in, making the atom smaller. As we go down a column, however, the atomic size increases, even though we're adding more protons to the nucleus, and that's simply because we're adding an additional energy level. So for example, in the second period, the electrons are going into the second energy level. Second period is, of course, the second row. The third period, we're going into the third energy level. If I'm standing on the third energy level and I'm looking at the second energy level, I'm looking in. So the third energy level surrounds the second energy level. Therefore, as we go down a column, we're adding an entire layer of electrons, so the atoms are going to get much, much larger. And if you look back a couple of slides, you can see that. So putting this together into things that we can actually measure, you can say, an atomic radius, by the way, is measurable. But anyway, ionization energy is the amount of energy required to move an electron from an atom. If you look at sodium, for example, pulling an electron out makes it go from sodium to the sodium ion, and of course an electron. If you look at the configurations, you see how we go to an empty valence from 3s1 down to 2s2, 2p6. So as you go across a row or down a column, would you expect the ionization energy to increase as we go across a row or decrease? Same with down a column. Think about what holds the electron in and how that varies across a row and down a column. Hit pause on the video, see what you can figure out, and then go ahead and hit play and go to the next slide. All right, and again, as I'd said, the only thing preventing an electron from leaving the atom is the nucleus. Across a row, the atoms are going to get smaller, therefore the nucleus is closer to the electrons. Remember from Coulomb's law, as the nucleus gets smaller, the force of attraction between the nucleus and the electrons is going to get larger, or just thinking intuitively, as things are closer together, they interact more strongly. Therefore, it would be harder to remove an electron. Therefore, the ionization energy would tend to increase. As we go down a column, the atoms are getting bigger. So for the same reason that ionization energy increases going across a row, it's going to decrease going down a column. Okay? Bigger atoms, so on. This is a summary on this slide. So you can see as we go down a column, the ionization energy decreases. As we go across a row, it increases. So you would expect the upper right-hand corner to have the highest ionization energy. So who cares about ionization energy? Well, what's trying to lose electrons? Metals. So if you look at metal reactivity, metals trying to lose electrons. The easier it is to lose electrons, the more reactive it should be, and vice versa. Harder to lose electrons should be less reactive. So as the bullet points say, as we move across a period, across a row, ionization energy increases, which means it's harder to lose electrons. Therefore, you would expect metal reactivity to decrease. Going down a column, atoms get larger, therefore the ionization energy decreases, making it easier to lose electrons. Therefore, you would expect metal reactivity to increase as you move down a column on the periodic table. One thing I want to remind you of is if you just memorize or understand how charges interact, how the radius varies, and then the definitions, you can figure out the rest of this. Memorizing this would be very easy to get things backwards or flip them around in your head. But if you just think about what's going on with the charges and the distance between them, most of this is stuff you can figure out on your own. All right, so metallic character or metal reactivity is another way of saying it, should increase down and decrease to the right as it's shown in this slide. So try this on your own. Give yourself a minute. In each pair, circle the more reactive metal. Okay? Hit pause, try it on your own, and then when you're ready, you can go ahead and hit play and go to the next slide. All right, and as you can see, okay, the one potassium is further to the left than calcium, therefore it should be a more reactive metal. Going down a column, magnesium and calcium are in the same column. Lower down in the column, more reactive. All right, let's look at attraction for additional electrons. In the old days, this was called electron affinity. We don't typically use that term as much, but this would be in equation form, chlorine becoming the chloride ion. I put in the configurations so you can get a feel for what's going on. If you look back at the metal reactivity slide and how sodium reacts, you can see that sodium is going to, when it loses electron, a more stable state, a noble gas configuration. When the nonmetal gains electrons, again, a noble gas type of configuration. So think about this as we go across a row. Would you expect attraction for electrons to increase or decrease? Same with going down a column. As before, hit pause and give yourself a minute, and then go ahead and go to the next slide after you hit play. So on the next slide, I hope you didn't take too long. Okay, remember the only thing that can pull an electron in is the nucleus, which is the same thing that holds electrons in. Once again, if you understand what's going on with charges, across the row the atoms get smaller. Therefore, the nucleus is closer to the electrons, should hold on to them more tightly. And of course, going down the column, one would expect the nucleus is further away, right? Weaker attraction, and attraction for electrons should decrease. Excuse the background noise. Apparently someone's walking by my house. Okay, so I drew this on. You can see attraction for electrons decreases down a column and increases to the right. So thinking in terms of nonmetal reactivity, okay, nonmetals tend to gain electrons. So that means that the stronger attraction for additional electrons, more reactive for nonmetals, and weaker attraction for additional electrons, nonmetals should be less reactive. So once again, putting things together as we move across a period, across a row, attraction for electrons increases because the atoms get smaller. That means it's going to be easier to gain electrons. Therefore, nonmetals should become more reactive, moving to the right. And down a column, atoms get larger, the nucleus is further away. Therefore, they should be less adept or be harder to pull electrons in to bigger atoms. Therefore, you would expect nonmetals to decrease as we go down a column. So like we did before, give this a go. These are nonmetals. Okay. Hit pause and go to the next slide and come back. Nice job. I figured you guys would get it right. All right, so again, between oxygen and nitrogen, if you look at the periodic table, oxygen is further to the right, smaller atom. Therefore, it should be easier to gain electrons. Therefore, it's more reactive. Fluorine and chlorine are in the same column. So in the same column, we look at the size of the atom as we go down a column. Fluorine is a smaller atom. Smaller atoms attract electrons much better than bigger atoms. All right. Last trend that we'll talk about is electronegativity, which is very similar to, it is actually another way of looking at attraction for electrons. Electronegativity, the only difference is it's attraction for electrons in a bond, and the next video will be, or next PowerPoint really, will be about the types of bonds, and so that'll make a little bit more sense when we apply it there, but it's a good time to talk about it here. Okay, it's still attraction for electrons, so one would expect that it would have the same, follow the same pattern, and it does. Moving to the right, atoms get smaller, attraction for electrons increases. Moving down a column, atoms get bigger, attraction for electrons should decrease. That's the end of the slide, so hopefully you've gotten what you need out of this. You should be able to do homework number 7 from this information. This is the last set of information that will be on the next exam.